Today, I'll tell you about what we believe is a tremendous opportunity for standard of care data in informing discovery. So the data modality that that I would like to tell you about is histopathology, specifically your standard H&E slides. And what we love about H&E slides is that they are very much routinely collected from every solid tumor patient, pretty much anywhere around the world. And increasingly, although certainly far from universally, they are collected in digital form. These data contain a surprising amount of information at multiple biological scales, starting from intracellular structure, cell-to-cell interaction, all the way to much higher level structures such as vasculature. And when you give these images to a pathologist, typically what comes out is 2 or 3 ordinal numbers. And what I hope to show you today is that there is a tremendous treasure trove of information that is hidden within these data that is currently going untapped. So there's certainly a lot of work going on in incorporating digital pathology into clinical care. What typically happens is that there is a specific supervised task that the machine learning is intended to solve. So, for example, predicting survival or predicting tumor mutational burden. And in each case, a model is trained specifically to that task, and that is intrinsically therefore limited by the availability of training data for that particular task at sufficient scale. What we aim to do is to actually initially let the data speak for themselves. So we take a large amount of histopathology data and we apply the techniques of self-supervised deep learning, which have been so impactful in other forms of data modality, whether it's text or images on the web, protein sequences or others, and learn basically what we call an embedding or a low dimensional featurization of these very high dimensional images into something that is much more concise, but still captures much of the semantic content of those images. That embedding, because of its because it is so much more concise and yet contains the information, can then be overlaid with much smaller data sets that contain relevant covariates, whether those are clinical covariates, such as risk or response to treatment, or molecular covariates that give us insight on the underlying biology. And those together, because the data is now so much more concise, allow us to uncover associations that would be invisible in the original space. So one of those areas that we've been privileged to work in is in partnerships with Genomics England, and you've heard Probs alluding to this partnership in his presentation. We've taken the self-supervised embedding and basically simply by doing a similarity search in embedding space are able to allow the user to upload some number of images that they find of interest and retrieve ones that are semantically similar. And what I'm showing you here is that semantic similarity in an entirely unsupervised way allows us to uncover cancer types and subtypes, as well as much finer grained structure, which we're not able to show in this visualization. But there's a lot more than just that. So, for example, what we show here is the ability to take the information within these embeddings and inform our understanding, our ability to predict cancer outcomes. What you see here, this is in breast cancer, but we've done this for most cancer types where we were powered for this type of discovery. On the left, you see a standard Kaplan-Meier curve that shows the clinical risk using the standard clinical covariates used in the standard of care, age, sex, IHC subtypes, and so on. And you can certainly see separation between high risk and low risk using those covariates. On the right-hand side is what you get when you add the information from the embedding into the prediction of the clinical outcome. And you can see that the separation is much clearer with a much better p-value and a much better goodness of fit. What I think is even more interesting, however, is this plot over here. This is a scatter plot where the points are patients, and the x-axis is that same clinical risk score that drove the Kaplan-Meier curve on the left, and the right-hand side is that additional information that you get from the embedding on top of the clinical risk score. And what's noteworthy is that you can see that those are effectively uncorrelated, which means that the information that is derived from the H&E embedding is entirely uncorrelated with what the pathologist looks for when they are ascertaining clinical risk. So that is interesting in itself, but I think, but it's only the beginning of the information that can be extracted from the H&E data when we overlay small amounts of additional molecular covariates, you can extract a significant amount of additional insight from each and every one of those H&E samples. So what we do here is we take that same self-supervised embedding that drove the Kaplan-Meier curves, we overlay, in this case, a certain amount of somatic alterations for those patients, and we train a simple linear model to predict, in this case, somatic alterations. And what you see here is that we're able to predict these somatic alterations from the H&E alone at an accuracy of 90 to 95%. This is in breast cancer, but again, this is just an illustration. We've done this across multiple somatic alterations across multiple cancer types. Since our goal is not to just make predictions, but really to partner with a pathologist, we've also created this visualization, which you can think of as a deep fake for pathology. It takes the embedding and basically generates synthetic pathology images, which in this case are each of those is a tile that we transition in embedding space from, say, a CDH1 negative to a CDH1 positive tumor, keeping everything else constant, allowing the pathologist to really home in on the subtle differences in the image that are driven, say, by CDH1 mutation. And what you see on the right is the pathologist post hoc interpretation of what it is that they see in those images, saying, oh yeah, we can see that the machine learning is picking up on, for example, progression from ductal to lobular carcinoma. This is not an input to the model, rather it's a post hoc interpretation by the pathologist at the end of the day. Somatic alterations, again, is only one aspect. What you see here, before we showed you breast cancer, this is ovarian cancer. You can see on the left-hand side, again, predictions of somatic alterations, showing that this applies not just in breast cancer, but what you see on the right, again, in ovarian cancer, is the ability to predict a set of well-characterized RNA subtypes that are very significant from a clinical outcome perspective. And you can see that those too are predicted from the H&E alone at an accuracy of above 0.8. But it's so the ability to predict RNA subtypes is nice, but it turns out we could actually predict even more than just RNA subtypes. What you see here is the ability to predict actual RNA transcriptional profiles from the H&E alone. So you can see here, this is, again, predictions of obviously on held out test patients. Each row is a patient, each column is a gene, and you can see in the plot on the right, on the top right-hand side, the observed RNA-seq data relative to the predicted RNA-seq data, and at the bottom right you see the scatter plot for the correlation coefficient across the genes, and you can see that it's actually quite accurate. RNA-seq is only the beginning. We've also worked with a data set that is much more challenging, ATAC-seq. This is a very high-value assay. It measures chromatin accessibility of the genome. As such, it is able, better than RNA-seq, to identify patterns relevant to lowly expressed driver genes, as well as other epigenetic alterations that are not associated with coding genes. This data is very rarely collected, certainly not as part of the standard of care, but because it was collected from 400 samples within TCGA, we're able to take the same embedding and train a model on ATAC-seq. And you can see over here that you can get the same kind of predictive accuracy that we were able to show for RNA-seq, despite the small size of the data set. Again, top right plot is actual ATAC-seq. On the right-hand side, predicted ATAC-seq for held out test patients. And at the bottom, you can see a correlation of, again, very, very significant correlation across all of the ATAC-seq peaks, providing us with, again, significant insight on the molecular processes that exist in these tumors from the H&E alone. And from that, we can now start to ask all sorts of questions that we were not powered to ask at any previous time. If you have 400 ATAC-seq patients, you certainly cannot ask questions like which ATAC-seq peak is associated with survival. But if you can impute, for example, the ATAC-seq signature or RNA-seq signature across tens of thousands or even hundreds of thousands of patients, all of a sudden you can ask which peak is associated, say, with survival outcomes. And what you see here is on the left, the genes that are most associated with survival in breast cancer, on the right-hand side with triple-negative breast cancer, the number of triple negative breast cancer for which we had ATAC-seq annotated or measured was about 10, imputed on a very large cohort. All of a sudden we have hundreds, so we can actually identify genes that have a very significant hazard ratio for survival. Now, of course, this doesn't necessarily identify something that is a target of an interventional target because we don't necessarily have ascertainment of causality. But here, for example, is the ability to overlay an additional source of information, in this case, somatic alteration, on top of those potential targets. And what you see here is that in these targets, this is in TCGA, there is significant support in somatic mutations in that many of those genes are actually amplified in cancer in a way that is quite statistically significant. This is the red patterns that you see in this image, suggesting that there is actually a benefit to the tumor in amplifying those genes, suggesting that they might actually play a causal role in cancer processes. So this is my last slide, and I hope that I've convinced you that you can truly scale the impact of the human cohorts that are out there with machine learning on high content data, specifically in this case, histopathology data that is collected as part of the standard of care, overlaying it on top of these incredible resources, these large registries, with the use of multimodal machine learning is able to identify really critical biological insights in terms of stratifying patients, in terms of potentially predicting drug response, identifying subtypes that are more likely to be responsive than others, and even presenting us with therapeutic hypotheses on novel targets and novel patient populations. And so this is truly a transformative resource when juxtaposed with the biobanks that are out there. And thank you all very much. I will stop here.